Let's talk about the intermediate value theorem. The book, and a lot of books will do this, where they give kind of a watered down version, or really what it is it's a very narrow application of the intermediate value theorem. So I'm going to start off with the real thing. The intermediate value theorem, abbreviated IVT, tells us that if f is a continuous function on the domain a to b, and that there is a value L between f of a and f of b, that would be a y value between f of a and f of b, then there must be a c between a and b, meaning the x value c between a and b, such that f of c is equal to L. Now this sounds very complex, but I promise you it's really not that hard. So let's take a look at what this picture is saying. So I don't know exactly what the function is. It's just any continuous function, which means it's attached. There's no jumps, there's no holes, no disconnects. And I don't know if it's increasing, decreasing. I don't know where it is on the axis, but just to get an idea in my head, I'm going to just sketch this little wiggle. Again, I don't know that it's wiggling. It could be a straight line. The thing I know is it is attached. It could be going down, but the idea is going to be the same. What I am told is that I have an L value between f of a and f of b. So let me define f of a to be less than f of b. Again, why do I know that's true? I don't. This is just one possibility. And I know that there's some L value between them. Well, if we think about how we got to that f of a, there was some a value that when we plugged into our function gave us a f of a. F of b, same idea. There's some x value of b that when I plug that b in, I get to my y value of f of b. What my theorem is telling me is that if we have that space between f of a and f of b, and when we do, as long as f of a and f of b are not the same number, there is going to be a number in between. There has to be a way for me to get that to that number, and we're calling that value c. There has to be an x value that will get me to that L. Obviously, this would not be true if the function wasn't connected. I think we could just have a big hole right here, meaning we never actually get to that number, or we get to it in kind of a choppy way. So we do have to know this is a continuous function. So it doesn't matter if I draw this thing increasing, decreasing, which quadrant I draw this in, picture will always kind of be the same, where if I know that there is that L value stuck between the f of a and f of b, there has to be an x that gets me to that L if we have a continuous function. Now, like I said, our book and a lot of books apply it in a much narrower way. Our application of the intermediate value theorem states if f is a continuous function over the domain a to b and f of a and f of b have different signs, then there must be a zero between a and b. So, very similar idea. We still have that y value, these y values are not the same, but this time we're told particularly they have different signs. So again, I'm going to just choose a function to represent. So I have this sort of curve here, could be doing whatever, right? But I see that my f of a is negative and my f of b is positive. Could it have been opposite? Absolutely. And so of course there has to be an a value that gets me to that f of a, there has to be a b value that gets me to that f of b, and there has to be all the L's in between f of a and f of b. Because f of a is negative and f of b is positive, that means in particular that 0 has to be between them. So obviously there is a c between a and b that will give us 0, meaning that there's a 0 of the function. And we'll talk about some polynomials. So if we're talking about a polynomial, there has to be a root of the function between a and b. So let's take a look at an example. Here we have a function f of x is equal to 2x cubed minus 4x plus 1. This function is continuous. We know this is a polynomial function. It's degree 3. We know it would have a couple bends to it. We don't know exactly what it looks like in terms of its zeros because we don't know how to factor this right now, right? So we don't know how to factor it, so we're kind of stuck. We don't know where the zeros would be. But what we can do is we can use our intermediate value theorem to help us narrow down where they are. So let's start with this question A. Let's determine if there is a 0 between x is equal to 1 and x is equal to 2. Well, to do this, I need to consider the signs of the y values. So I'm going to look at f of 1, I'm going to look at f of 2. F of 1 will have 2 times 1 cubed minus 4 times 1 plus 1. So this would be 2 minus 4 is a negative 2 plus 1 is a negative 1. F of 2 will have 2 times 2 cubed minus 4 times 2 plus 1. 2 cubed is 8 times 2 is 16. Minus 8 will be 8 plus 1 is 9. So what that tells me is there must be a 0 between x is equal to 1 and 2. The intermediate value theorem tells me that. Now, let's draw this out just to kind of think about what we've said. f of 1, f of 2. Don't know exactly what the function around them looks like, but I know here at 1 we have -1, at 2 we'd have a value way up here at 9, right? Just breaking my scale a little bit. The only way I can connect these 2 points on a continuous curve is if I cross the axis. Again, that might not be drawn the correct way. It could be curving more like this, it could be a straight line, or actually what it could do is it could cross over multiple times. I don't know, right? We don't know what it's doing. We haven't said anything about there's exactly 1, 0. We haven't said it's taking a straight line path or a curve down, a curve. We're just saying there must be a 0 between 1 and 2. That's all we're saying. Let's take a look at the next one. X is equal to 2, x is equal to 3. I'm going to do the same thing, but I'm going to do it with the 2 and the 3. Well, the 2 we already found, that was 9 from the previous example. 3 I've got to work as a new problem. And so 3 cubed is 27, double it we get 54, minus 12 would be 42, and add one more we get 43. And so here we see we go from a positive to a positive. The signs have not changed. So I might have the inclination for just half a second to say no. But guess what? That would be completely wrong. Because our theorem never said that if the signs don't change, there is not a 0. We can't assume that. We're putting words in there that just don't exist. The theorem told us if the signs change, then there has to be a 0. It doesn't say anything about the lack of existence or something not existing. Because if we think about this picture, f of 2 we have 9, and again just kind of ballparking these y values 9, and then at f of 3 we have a much higher value of 43 way up here, 43. How could I connect these 2 points? Could I connect them so that it never crosses the x-axis? Absolutely. Could I cross them so that they do cross the x-axis? Absolutely. Right, and I could have crossed it any number of times, just like this one. We said we could have crossed this one any number of times to get to that next point. And so at this point, we can't say that to connect those 2 points, that there is not a 0 between them. We can only say, we don't know. And that's the right answer for right now. Let's do the next one. F of 0 and f of 1. So f of 0 is very easy. We just plug in the 0 everywhere. And we have 0 minus 0 plus 1. That gives us positive 1. F of 1 we calculated in that very first step. That was a negative 1. So here once again we can say there must be a 0 between 1 and 2. Between 0 and 1. Again, using the intermediate value theorem, we know that is true for certain. Now here's kind of the crazy thing. I'm going to take this a step beyond where you might be. So depending on where you are in your studies and where you are in your reading, in terms of applying the intermediate value theorem, these 3 statements are true. We know all 3 of these things are true at this point. But let's build on our knowledge a little bit. So this is taking it to the next level. With polynomials, we know that this is a degree 3 polynomial. And with polynomials, we know, or we're going to come to learn, if we haven't seen it already, that the degree tells us the number of roots of the polynomial. So the degree being 3 tells us there must be 3 roots to this polynomial. Now, what's true about those roots? They could be real, meaning they actually cross the x-axis. So, something like that first picture, that would be a real root. It could be that we have imaginary roots. They don't actually show up on the axis. We haven't crossed the x-axis. But if we were to plug in values to solve this function, we would find that there are values that would solve it. So we can have real zeros, we can have imaginary zeros, and then we can have zeros with multiplicities that are higher than 1. So that would be something like, try that a little bit better, the x cubed function passes through with multiplicity of 3, and so there would be 3 zeros there, even though it's only 1 unique 0. So again, there's some more information tied up in just these roots than strictly saying there's 3 unique answers. But we're going to hold off on that idea for just a second. We don't really need that here, because what we've already found is that because we're crossing that x-axis, we found that there is a 0, meaning there is a real root between 1 and 2. We have found that there is a real 0, a real root between 0 and 1. So between 0 and 1, we've already accounted for 1, 0 in that span. That one would actually be on the way up if we're doing this incorrect, I believe. And then between 1 and 2, there's another 0. So we have 1 0 accounted for here. We have 1 0 accounted for here. And that means in all the rest of the universe, everything outside of 0 to 1 and 1 to 2, there can only be one more 0. Well, it could be imaginary, but it could be real. So we said at the beginning, the first time we did this 2 to 3 problem, that we didn't know between 2 and 3. We weren't sure what was going on between these 2 points. But remember, the only way we could have had a 0 is if it dropped down, crossed, and then crossed again. Meaning, there was just 2 x-intercepts. There was 2 zeros here. That's impossible. We said that there is only one more in the entire universe. We can't have 2. You might say, well, what if it were to go down, touch the x-axis, and turn back up? Again, that gets into that idea of multiplicity. And so that would be one unique 0 with a multiplicity of 2, which is still the idea of 2 zeros. So actually now, this we don't know, we can come back and change our answer to no, because we found there were only 3. And we know where 2 of them are. So again, that might be getting a little bit more advanced than what we need for right now. Right now, we are just testing to see, is there a 0? Can we tell using the intermediate value theorem that there's a 0 between 1 and 2? Yes, we can. Between 0 and 1? Yes, we can. Between 2 and 3? The intermediate value theorem doesn't tell us anything. The intermediate value theorem tells us nothing about between 2 and 3. The signs stay the same. We don't know. But if we apply some other knowledge to that, we may be able to figure out if there's actually additional ones in there or not.